Hello everybody, get ready to do lesson 11.1 part 3 classwork for pre-calculus math today. And for today's lesson, part 3, 11.1 introduction to limits classwork, you got 12 points here to go into your notebook and 40 points will go on your classwork sheet. Have those out in front of you, name, date, period, and then due date here for homeschoolers and onliners. And for today's bell work, teachers and students, simplify these rational expressions. Again, we have one of those. Give your students 5 minutes. Pause your video for 5. Okay, welcome back everybody for today's bellwork solutions. So to simplify this, x cubed plus 27 over x squared plus x minus 6, we need to factor out an x plus 3 here out of this expression. We come up with this quadratic x squared minus 3x plus 9 over x plus 3x minus 2. These will factor here. You're left with x squared minus 3x plus 9 over x minus 2. And x cannot equal negative 3 for up here. And then for down here, x cubed minus 8 over x squared minus 4. You factor out x minus 2 out of your numerator, and you end up with x squared plus 2x plus 4 over x minus 2, x plus 2. And then these will factor out, and then you're left with x squared plus 2x plus 4 over x plus 2. And then x cannot equal 2. Into today's lesson. Continuing on here. Example 8, oscillating behavior. Discuss the existence of the limit of as x approaches 0 for sine 1 over x. Now, this is the graph of f of x equals the sine of 1 over x. So with that situation, you can see that as x approaches 0, f of x oscillates between negative 1 and 1 here. You have this oscillation. So the limit does not exist because no matter how close you are to 0, it is possible to choose values of x1 and x2 such that sine 1 over x1 could equal 1, and then sine of 1 over x2 could equal negative 1. So it could be either one of those, as indicated here by the table. So for sine 1x, we have 1, and then negative 1, 1, negative 1, 1, negative 1. So you have different values here for each time that you proceed here. Here it's 2 over pi, and down here it's 2 over 5 pi. So we have different values for the same input here. We have different values here. Limit does not exist. And then this would be how it would look on your graphing calculator here. So okay, yeah, so as indicated by the table, the limit does not exist. So let's try one here. Use the graph to find a limit if it exists. If the limit does not exist, explain why. So we have the limit as x approaches 0 for 2 cosine pi over x. And again, we get an oscillation kind of graph happening there. So the limit does not exist because f of x oscillates between 2 and negative 2 here. So negative 2 down here and then 2 up here. So you have an oscillation there that happens. Examples 6, 7, and 8 show 3 of the most common types of behavior associated with the non-existence of a limit. Conditions under which limits do not exist. The limit of f of x as x approaches c does not exist under any of the following conditions. F of x approaches a different number from the right side of c than it approaches from the left side of c. We saw that in example 6. F of x increases or decreases without bound as x approaches c. We saw that in example 7. And then f of x oscillates between two fixed values as x approaches c, and we just saw that in example 8. Properties of limits and direct substitution. you have seen that sometimes the limit of f of x as x approaches c is simply f of c. In such cases, it is said that the limit can be evaluated by direct substitution. That is, the limit as x approaches c for f of x equals f of c. You can substitute c for x. There are many well-behaved functions, such as polynomial functions and rational functions with non-zero denominators that have this property. Some of the basic ones are included in the following list. So, basic limits. Let b and c be real numbers and let n be a positive integer. So you have one here, limit as x approaches c, b would equal b. And then the limit as x approaches c, x equals c. And then the limit as x approaches c for x to the nth would equal c to the nth. And then the limit as x approaches c for the radical x to the with an index of n here to the root to the nth root of x equals the nth root of c for n even and c greater than 0. Trigonometric functions can also be included in this list. For instance, the limit of as x goes to pi for sine x equals sine pi would equal 0, and the limit as x approaches 0 for cosine x equals cosine 0, which would equal 1. So by combining the basic limits of the following operations, you can find limits for a wide variety of functions. Properties of limits. Let b and c be real numbers, let n be a positive integer, and let f and g be functions with the following limits. So the limit as x approaches c for f of x equals L, and the limit as x approaches c for g of x equals k. One scalar multiple, you have the limit of x approaches c for bracket b of f of x, close bracket, equals BL. In this case here, it would be BL in this situation there. And then a sum or a difference will be the limit as x approaches c for bracket f of x plus or minus g of x equals L plus k. So you can do a sum or difference from that. And then the product for the limit as x approaches c for bracket f of x g of x would equal LK. So, and then we have a quotient here. The limit as x approaches c for f of x over g of x would equal L over k, provided k does not equal 0. And then we got a power for the limit as x approaches c for bracket f of x to the nth power could equal L to the nth power. So let's try one. Direct substitution and properties of limits. So we have a situation here where we just directly substitute in. As x approaches 4, we just stick that into our expression here and we get 16. And then for the limit or scalar multiple, we have 5x here. For as x approaches 4, we just plug in 4 here in this expression. Or basically you move this back in here and we go 5 times the limit of x as x approaches 4. It would be 5 times 4, which would equal 20. And then here we have a quotient property. The limit as x approaches pi for tan x over x would equal the limit as x approaches pi for tan x over the limit as x approaches pi x would equal 0 over pi, which would equal 0 by using the quotient property of and then the limit here for as x approaches 9 radical x would equal radical 9, which would equal 3. We directly substitute. And then here the product property, the limit as x approaches pi for x cosine x would equal the limit of x as x approaches pi times the limit of cosine x as x approaches pi. And then we just use our product property here. It would be pi times cosine pi, which would equal negative pi. Cosine pi would be negative 1. And then here the sum and power properties will be the limit as x approaches 3 for the quantity x plus 4 squared would equal the limit of x as x approaches 3 plus the limit of x as x approaches 3 of 4. And then we can just add those values, and that quantity will be squared. It'll be 3 plus 4 squared, it'll be 7 squared, it would equal 49. So let's try one here. In this one up here, we got find A, B, C, and D here. So limit A here is as x approaches 2 for f of x, and it's for f of x equals x cubed and g of x equals radical x squared plus y over 2x squared. So for A, we just have f of x here as x approaches 2. So we can directly substitute into that. We get 8. 2 cubed would be 8. And then B here would be the limit as x approaches 2 for g of x. This one down here is a little bit more complex, but we substitute in and we end up with 3 over 8 for this one. 2 squared plus 5 over 2 times 2 squared. And then for C, as the limit as x approaches 2 for f of x g of x would equal 8, because we've already done our f of x up here, times g of x, which would be this. 8 times 3/8 would equal 3. And then D here will be g of x minus f of x. So g of x minus f of x would be 3/8 minus 8 would be the negative of 61 over 8. And students, do the same thing down here for yours, independent practice down here. Limits of polynomial and rational function. So 1, if p is a polynomial function and c is a real number, then the limit as x approaches c for p of x would equal p of c. And c is a real number here. And then 2, if r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c does not equal 0, then the limit of as x approaches c for r of x equals r of c would be the same thing as p of c over q of c. Example 10, evaluating limits by direct substitution. Find each limit. So A here as x approaches -1 for x squared plus x minus 6. So to evaluate the limit of a polynomial function, use direct substitution. So we just plug in here -1 squared plus -1 minus 6, and this will be -6 for this one. And then for B here, we have as x approaches -1 for x squared plus x minus 6 over x plus 3. The denominator is not 0 when x equals -1, so you can evaluate the limit of the rational function using direct substitution. So when we do that, when we substitute in, we end up with -6 over 2 or -3 for B. Let's try one now. Find a limit by direct substitution. So the limit as x approaches -3 for 2x squared plus 4x plus 1. Students, this is yours down here. So for up here, we just substitute in and we end up with 7 here. 2 times the -3 squared plus 4 times -3 plus 1 would equal 7. And that is your 11.1 Part 3 Pre-Calculus Math classwork lesson. My email, animatedpowerpointmathvideo@aol.com for course materials and/or questions. Thank you very much.